last part, yeah, the last part of this drive, the AC drive. We have already discussed the DC drive on Monday. Yeah, so today we are looking into the DC drive. Uh, wait, today I plan to use my recorder video. It will be a little bit robotic. Not like what I'm presenting. Okay, but it's okay. Also, mainly the advantages of this AC drive I have already mentioned to you on Monday. Yeah. Just that in this AC drive here, normally we can actually have two types: induction motor drive and synchronized motor drive. But we mainly focus only on the induction motor drive. Yeah. All right. Just give me a second. Let me call out the video file. Give me a second. Yeah. Who else haven't joined us? 1, 2, 3, 4, 5, 6, 7, 8. So there are two more. I just want to confirm with you. Is this was it Ying Xuan or Ying Xuan? Yeah. He already applied for deferment. Okay. So the deferment is for the entire subject, right? Yeah. Oh, okay, good. Thank you. By the way, who? Do you know that whether he? I haven't actually got time to look into your individual project. Your lab report. Who is with him in team, or do you include him inside for his this lab practical report? Okay. Because he didn't do the work, right? All right. Okay. Thank you, John. Okay, I will start the video now. It takes about 56 minutes, 55 minutes from now. Okay, thank you. Induction motor drive. Three-phase induction motors are commonly used in ASD, and they have three-phase stator and rotor winding. The stator winding are supplied with balanced three-phase AC voltages, which induce voltages in the rotor winding due to transformer action. It is possible to arrange the distribution of stator winding so that there is an effect of multiple poles. producing circular cycle of magnetic motive force around the air gap. This field establishes a spatially distributed sinusoidal flux density in the air gap. The speed of rotation of the field is called synchronized speed, or omega s, and is defined as in equation number 1 here, equal to 2 omega over p. P is the number of poles and omega is the supply frequency in radian per second. If a stator phase voltage Vs is a sinusoidal form, then it produces a flux leakage, which is given in equation 2 here. The induced voltage per phase in the rotor winding is given in equation 3 here, where Nr is the number of turns on each rotor phase. Omega m is the angular rotor speed or frequency in hertz. Delta is the reactive position of the rotor. Er is the IMS value of the induced voltage in the rotor per phase. En is the peak induced voltage in the rotor per phase. And S is the slip, which is defined in equation 4 here. If we rearrange it, we can find the motor speed omega m equal to omega s multiplied by 1 minus s. The equivalent circuit for one phase of the rotor is shown in the figure 16.1a, where R is the resistance per phase of the rotor winding. XR is the leakage reactance per phase of the rotor at the supply frequency. ER represents the induced IMS phase voltage when the speed is 0, meaning that the slip S equal to 1. This is the one. The part B, or the figure B here, shows the combination of the stator and rotor circuit, and the figure C shows the complete equivalent circuit or the complete model of the induction motor. Rotor current is given in equation 5 and 5a, where RR and XR are referred to the rotor winding. The per phase circuit model of induction motor is shown in figure 16.1b just now, where RS and XS are the per phase resistance and leakage reactance of the stator winding. The complete circuit model is shown in figure 16.1c, where Rm represents the resistance for excitation loss and Xm is the magnetizing reactance. Rr prime and Xr prime are the rotor resistance and reactance referred to the stator. Ir prime is the rotor current referred to the stator. There will be stator core loss when the supply is connected, and the rotor core loss depends on the slip. The friction and windage loss P no load exists when the machine rotates. The core loss PC may be included as a part of rotational loss, the P no load. The rotor current IR and stator current IS can be found from the circuit model in 16.1c, where RR and XR are referred to the stator winding. Once the value of the IR and IS are known, the performance parameters of the three-phase motor can be determined as follows. Stator copper loss, rotor copper loss, core loss, gap power, and developed power are given in this page here from equation 6 to equation 11. The developed torque is given in either equations 12 or 12a here. Input power is in equation 13 or 13a. The efficiency is in equation 14. If Pg is much greater than the Pc plus the Psu, and also the Pd is much greater than the P no load, the efficiency can be approximate in equation 14a here, which is equal to 1 minus S. The value of Xm is normally large. However, Rm is much larger, and it can be removed from the circuit model to simplify the calculation. Also, if Xm squared is a lot greater than the Rs squared plus Xs squared, then the voltage Vs is approximately equal to the Vm, and the magnetizing reactance Xm can be moved to the stator winding to simplify further. This is shown in figure 16.2. This is the circuit here. So initially it was in here. So if we remove the Rm, and this value is much smaller as compared to the rest, so the Xm can be shifted in front to place it here. By doing so, we can find the input impedance Zi in equation 15 here, which is the Xm parallel to the rest of the circuit. And also the power factor angle of the motor can be obtained in equation 16. The rotor IMS current IR prime can be obtained in equation number 17 here. Substituting IR prime for this equation into equation 9, which is the gap loss, the gap power, and then put the gap power into the equation 12a for the developed torque. The developed torque Td can be written in equation number 18 here. If the motor is supplied from a fixed voltage and the fixed constant frequency, the developed torque is a function of the slip, and the torque speed characteristic can be determined from the equation 18 here. A typical plot of developed torque as a function of slip or speed is shown in figure 16.3 here. This is the one. The operation in the reverse motoring and regenerative braking is obtained by the reversal of the phase sequence of the motor terminal. The reverse speed torque characteristics are shown by dashed line. There are three regions of operation. Number 1, motoring or powering, where the slip is between 0 to 1. Regeneration, S is less than 0. And number 3, plugging, the slip S is in between 1 to 2. In motoring, the motor rotates in the same direction as the fuel, and as the slip increases, the torque also increases, while the air gap flux remains constant. Once the torque reaches the maximum value, Tm at slip equal to Sm, the torque decreases with the increase in slip due to reduction of the air gap flux. In regeneration, the speed omega m is greater than the synchronized speed omega s, with omega m and omega s in the same direction, and the slip is negative. Therefore, the ratio of Rr over S is negative. This means that power is feedback from the shaft into the rotor circuit and the motor operates as a generator. The motor returns power to the supply system. The torque speed characteristic is similar to that of motoring, but having negative value of torque. In reverse plugging, the speed is opposite to the direction of the field and the slip is greater than unity. This may happen if the sequence of the supply source is reversed while forward motoring, so that the direction of the field is also reversed. The developed torque, which is in the same direction as the field, opposes the motion and acts as braking torque. Because S is greater than 1, the motor current are high, but the developed torque is low. The energy due to a plugging brake must be dissipated within the motor, and this may cause excessive heat of the motor. This type of braking is not normally recommended. At starting, the machine speed is omega m, which is equal to 0, and slip s equal to 1. The starting torque can be found from the equation number 18 by setting s equal to 1. That should give you the Ts equal to equation 19 here. The slip of maximum torque Sm can be determined by setting dTd over ds equal to 0, and from equation 18. That should give Sm equal to in equation 20. Substituting S equal to Sm into the equation number 18, that should give the maximum developed torque during motoring, which is also called pull-out torque or breakdown torque. The TMM is defined in equation 21 here. The maximum regenerative torque can also be found from the equation 18 by equating S equal to minus Sm, and TMR, which is the maximum regenerative torque, is shown in equation 22. If Rs is considered small compared with other circuit impedances, which is usually a valid approximation for motor more than 1 kilowatt rating, the corresponding expression become, for example, the Td is rewritten in equation 23. Ts, Sm, and Tmn are rewritten in equation 24 to 26 respectively. If we normalize it, the equation 23 and 24 with respect to equation 26, so the ratio of Td over Tmn is shown in 27, and Ts over Tmm is shown in equation 28. If S is smaller than 1, so your S squared is a lot smaller than the Sm squared, and equation number 27 become equation 29 here. By rearranging it, the omega m can be obtained in equation 30. It can be noticed from equation 29 and 30 that if the motor operates with small slip, the developed torque is proportional to slip and the speed decreases with torque. The rotor speed, which is 0 at the synchronized speed, increases due to the decrease in the ratio of Rr over S as the speed is decreased. The developed torque also increases until it becomes maximum at S equal to Sm. For S less than Sm, the motor operates stably on the portion of the speed torque characteristic. If the rotor resistance is low, Sm is low. The change of motor speed from no load to rated torque is only a small percentage. The motor operates essentially at a constant speed. When the load torque exceeds the breakdown torque, the motor stops and the overload protection must immediately disconnect the source to prevent damage due to overheating. It should be noted that for S greater than Sm, the torque decreases despite an increase in the rotor current, and the operation is unstable for the most motor. The speed and torque of induction motor can be varied by the following means. Basically, the three of them: the stator voltage, rotor voltage, frequency. Of course, current is also one of the major player here to to change the speed and also the torque. Taking an example 16.1 here, finding the performance parameter of a three-phase induction motor. A three-phase 460 volt 60 Hz 4-pole Y-connected induction motor has the following equivalent circuit parameters. Okay, so the RS, RR prime, XS, XR prime, XM are given. No load loss is equal to 60 watt. The rotor speed is 1750 RPM. Use the approximate equivalent circuit in figure 16.2 to determine the synchronized speed, slip, the input current if RS is neglected. So first of all, we need to write down what are the information given and convert the omega into radian per second from the frequency given, which is 377 radian per second, and also the rotor speed omega m convert it into radian per second as well. So from equation 1 you can obtain what is the omega s, which is equal to 188.5 radian per second. Equation 4 to solve the part B for the slip S equal to 0.028. Equation 15 to solve for the Zi, which is equal to this number here, and hence by using this number we can find what is the input current II, and the value is equal to 34.35 with an angle of minus 30.88 M. The power factor is equal to 0.858. From equation 13, the input power PI is equal to 23,482 watt. The power factor of the input supply is equal to the PFM, which is also equal to 0.858, which is the same as the motor power. This is because the supply is sinusoidal. In equation number 17, the IMS rotor current can be obtained here at 30.1 M. So the gap power PG from equation 9 can be obtained, which is given the value of 22,327 watts. The stator loss PRU is equal to 625 watt. Stator copper loss is equal to 1142 watt. TD from equation 12a that gives the value of 118.4 Newton meter. The PO can be obtained as well, which is equal to the 21,642 watt. For S equal to 1, the starting IMS rotor current IRS is equal to 150.5 amp, and from equation number 19, TS is equal to 82.9 Newton meter. In equation 20, SM is plus minus 0.1359. Maximum developed torque TMM is equal to 265.64 Newton meter. The maximum regenerative torque can be obtained based on the equation 22 that gives a value of minus 140.94 Newton meter. In equation 25, SM is equal to plus minus 0.1402, and from equation 26, TMM is equal to 342.2 Newton meter. Stator voltage control. Equation 18 indicates that the torque is proportional to the square of the stator supply voltage, and a reduction in stator voltage can produce a reduction in speed. If the terminal voltage is reduced to BVS, equation 18 gives the developed torque as shown in this equation here, where B is less than 1. Figure 16.4 shows the typical torque speed characteristic for various value of B. The point of intersection with the load define the stable operating point. In any magnetic circuit, the induced voltage is proportional to flux and frequency, and the IMS air gap flux can be expressed as in equation 31 here. This one, where Km is the constant and depend on the number of turns of the rotor winding. As the stator voltage is reduced, the air gap flux and the torque also reduce. At a lower voltage, the current can be peaking at a slip of 1/3. The range of speed control depends on the slip for maximum torque SM. For a low slip motor, the speed range is very narrow. This type of voltage control is not suitable for a constant torque load and is normally applied to applications requiring low starting torque and a narrow range of speed at a relatively low slip. The stator voltage can be varied by three-phase AC voltage controller, voltage feed variable DC link inverter, or PWM inverters. However, due to limited speed range requirement, the AC voltage controller are normally used to provide the voltage control. The AC voltage controllers are very simple. However, the harmonic content are high and the input power factor of the controller is low. They are used mainly in low power applications such as fan blower and centrifugal pumps. They are also used for starting high power induction motor to limit the inrush current. Example 16.2. Finding the performance parameter of a three-phase induction motor with stator voltage control. A three-phase 460-volt 60Hz 4-pole Y-connected induction motor has the following parameter that are given here. The no-load loss, P no-load, is ignored. The load torque, which is proportional to the speed square, is 41 Newton meter at 1740 RPM. If the motor speed is 1550 rpm, determine the loop torque. B. The rotor current IR. C. The stator supply voltage VA. D. The motor input current II. E. The motor input power PI. F. The slip for maximum current SA. G. The maximum rotor current IR max. H. The speed at maximum rotor current omega A. And I. The torque at the maximum current TA. Because the torque is proportional to speed square, so TL is equal to equation 32 here, which is given equal to Km omega m square. So from equation 32, TL can be obtained in the value of 32.5 Newton meter. From equation 10 and 12, the PD is equal to the equation 33 here. For the no load loss is ignored, IR is equal to 20.28 M. The stator supply voltage VA can be calculated based on the equation here, and that should give you the value of 137.82 watt. From equation 15, ZI is equal to this number here, and the current II is equal to 20 with the angle of negative 35.82 degree M. PFM is equal to 0.812, and from equation 13, the input power PI is equal to 7386 watt. Substituting omega m equal to this equation and TL equal to this equation into the equation 34 previously, the IR prime can be obtained in equation 36 here. The slip at which IR become maximum can be obtained by setting DIR over DS equal to 0. Thus will give the SA equal to 1/3 in value. Substituting SA equal to 1/3 in equation 36 here, that should give the maximum rotor current in this equation 38 here, and the value is 24.3 M. The speed at the maximum current can be obtained in this equation 39 here, which gives 1012 rpm. Also from equation 9, 12a and also 36, TA is obtained in equation 40 here, and the value is given to 19.45 Newton meter. Rotor voltage control. In a wound rotor, an external three-phase resistor may be connected to its slip ring, as shown in this figure here. The developed torque may be varied by varying the resistance Rx. If Rx is referred to the stator winding and added to RR, equation 18 may be applied to determine the developed torque. The typical torque speed characteristic for variation in rotor resistance are shown in this figure here. As the R increase, the torque is also decreased. This method increases the starting torque while limiting the starting current. However, this is an efficient method, and there would be imbalances in voltages and current if the resistances in the rotor circuit are not equal. A wound rotor induction motor is designed to have a low rotor resistance so that the running efficiency is high and the full load slip is low. The increase in the rotor resistance does not affect the value of maximum torque, but increases the slip at maximum torque. The wound rotor motors are widely used in applications requiring frequent starting and braking with large motor torque, for example, crank and hoist. Because of the variability of rotor winding for changing the rotor resistance, the wound rotor offers greater flexibility for control. However, it increases the cost and needs maintenance due to slip ring and brushes. The wound rotor motor is less widely used as compared with the squirrel cage motor. The three-phase resistor may be replaced by a three-phase diode rectifier and a DC converter, as shown in this figure here, where GTO or an IGBT operates as a DC converter switch. The inductor L, D, act as the current source ID, and the DC converter varies the effective resistance, which is equal to this equation here in 41, where K is the duty cycle of the DC converter. The speed can be controlled by varying the duty cycle. The portion of the air gap power which is not converted into mechanical power is called slip power. The slip power is dissipated in the resistance R. This one. Example 16.3. Finding the performance parameter of a three-phase induction motor with rotor voltage control. A three-phase 460 volt 60 Hz 6-pole Y connector one-rotor induction motor whose speed is controlled by slip power as shown in figure 16.6a, which is this one. The performance parameters are given in here. Okay, the turns ratio of the rotor to stator winding is equal to 0.9. The inductance LD is very large and its current ID has ignore ripple. The value of RS, RR, XS and XR for the equivalent circuit in Figure 16.2 can be considered negligible compared with the effective impedance of LD. The no-load loss of the motor is ignored. The losses in the rectifier, inductance LD and the GTO DC converter are also ignored. The load torque, which is proportional to speed square, is 750 Nm at 1175 rpm. A. If the motor has to operate with a minimum speed of 800 rpm, determine the resistance R. With this value of R, if the desired speed is 1050 rpm, calculate B. The inductor current ID, C. The duty cycle of the DC converter K, D. The DC voltage VD, E. The efficiency, and F. The input power factor of the drive. Solution is provided to you here. So if the VA is equal to the VS, which is equal to 460 over sub 3, that give you the value of 265.58 volt. P is 6, so the omega is equal to 377 radian per second at 60 Hz. Omega S is equal to 125.66 radian per second. So the equivalent circuit is shown in this figure A here, and it can be reduced to figure number 16.7b, provided that the motor parameters are ignored. Okay, so all those parameters ignored, so this further simplified into this. For three-phase rectifier, equation 4T relate to EI, and the V as VD is equal to this equation. That should give you the value in equation 44 here. If PR is the slip power, equation 9 give the gap power equal to this value, and equation 10 give the developed power as in equation 45 here. The total slip power is equal to this, and the PD equal to TL omega TL times omega m. Equation 45 becomes equation 46 here. Substituting VD from equation 44 in 46, that will solve the ID in equation 47. This indicates that the inductor current is independent of the speed. Equation 42 to equation 44, that should give in this equation 48 here. This is the slip S. The speed can be obtained from equation 48 as in 49 here, and also in 50. So the developed torque. So the load torque TL is equal to 347.67 Newton meter at 900 RPM. From equation 47, the corresponding inductor current ID is equal to 78.13 amp. The speed is minimum when the duty cycle K is 0, and equation 49 gives the minimum speed. And this should calculate the resistance R equal to 2.3856 ohm. In part B, at 1050 RPM, TL is equal to 598.91 Newton meter, and ID equal to 134.6 amp. For omega m equal to 109.96 radian per second, and equation 49 give this. By rearranging it, we can obtain the duty cycle K equal to 0.782. By using equation 4, the slip is then equal to 0.125. From equation 44, VD is equal to 69.9 volt. In part E, the power loss is equal to 9409 watt. The output power P out is equal to this equation that gives the value of 65,856 watt. The IMS rotor current referred to the stator IR prime is equal to 98.9 amp. The rotor copper loss is equal to 1291 watt, and the stator copper loss is equal to 1203 watt, and the input power is equal to 77,759 watt. The efficiency is 85%. F from equation 29, for n equal to 1, the fundamental component of the rotor current referred to the stator is equal to this equation, and after plugging the value, we obtain that the value is 94.45 M. IMS current through the magnetizing branch, IM is 43.54 M. The IMS fundamental component of the input current is given in equation 51 here, that gives the value of 104 M. The power factor angle is approximately by the equation 52 here, and it is equal to minus 24.74 degree. Hence, the input power factor is equal to 0.908. Frequency control. The torque and speed of induction motor can be controlled by changing the supply frequency. We can notice from equation 31 that at the rated voltage and rated frequency, the flux is the rated value. If the voltage is maintained fixed at its rated value while the frequency is reduced below its rated value, the flux increases. This would cause saturation of the air gap flux, and the motor parameter would not be valid in determining the torque speed characteristic. At low frequency, the reactances decrease and the motor current may be too high. This type of frequency control is not normally used. If the frequency is increased above its rated value, the flux and torque would decrease. If the synchronized speed corresponding to the rated frequency is called the base speed omega b, the synchronized speed at any other frequency become in this equation here. And also the slip S is equal to equation 56. The torque expression in equation 18 become in equation 57 here. The typical torque speed characteristics are shown in figure 16.9 for various values of beta. The three-phase inverter in figures 6.5a can vary the frequency at a fixed voltage. This is the figure 16.9. Yeah. R8 is ignored. Equation 26 gives the maximum torque at the base speed as in equation 58 here. The maximum torque at any other frequency is given in equation 59 here. And also from equation 25, the corresponding slip is equal to equation 60 here. Normalizing equation 59 with respect to equation 58, that should give in equation 61 here, and also in equation 62. From equation 61 and 62, it can be concluded that the maximum torque is inversely proportional to speed square, and Tm beta square remains constant, similar to the behavior of DC series motor. In this type of control, the motor is said to be operated in a fuel weakening mode. For beta greater than 1, the motor is operated as a constant terminal voltage and the flux is reduced, thereby limiting the torque capability of the motor. For beta in between 1 to 1.5, the relation between Tm and beta can be considered approximately linear. For beta with less than 1, the motor is normally operated at a constant flux by reducing the terminal voltage VA along with the frequency so that the flux remains constant. Example 16.5. Finding the performance parameter of a three-phase induction motor with frequency control. A three-phase 11.2 kW, 1750 RPM, 460 volt 60 Hz, 4-pole wide connected induction motor has the following parameter as shown here. The motor is controlled by varying the supply frequency. If the breakdown torque requirement is 35 Nm, calculate the supply frequency and the speed omega m at the maximum torque. So from equation 62, beta is obtained in this equation and has a value of 1.321. Omega s is equal to 498.01 radian per second. From equation 1, the supply frequency is equal to 158.51 Hz. From 60, the slip for maximum torque is then obtained based on this equation here. So the Sm is equal to 0.101 and the omega m is equal to 4275 RPM. Voltage and frequency control. If the ratio of the voltage to frequency is kept constant, the flux in equation 31 remains constant. Equation 59 indicates that the maximum torque, which is independent of frequency, can be maintained approximately constant. However, at a high frequency, the air gap flux is reduced due to the drop in the stator impedance, and the voltage has to be increased to maintain the torque level. This type of control is usually known as volt-hertz control. If omega s equal to beta omega b and the voltage to frequency ratio is constant, so that VA over omega s is equal to D in equation 63. The ratio D is determined from the rated terminal voltage Vs and the base speed omega b, which is given in this equation here in 64. Substituting VA from 63 into equation 57 previously, that should give the slip Sm equal to equation 65 here. The typical torque speed characteristics are shown in figure 16.10. As the frequency is reduced, beta decreases and the slip for maximum torque increases. For torque demand, the speed can be controlled according to equation 64 by changing the frequency. Therefore, by varying both the voltage and frequency, the torque and speed can be controlled. The torque is normally maintained constant while the speed is varied. The voltage at variable frequency can be obtained from three-phase inverter or cycle converters. The cycle converters are used in very large power application, example locomotive and cement mills, where the frequency requirement is 1/2 or 1/3 of the line frequency. Three possible circuit arrangements for obtaining variable voltage and frequency are shown in figure 16.11. In 16.11a, the DC voltage remains constant and the PWM technique are applied to vary both the voltage and frequency within the inverter. Due to diode rectifier, regeneration is not possible and the inverter would generate harmonic into the AC supply. In figure 16.11b, the DC to DC converter varies the DC voltage to the inverter and the inverter controls the frequency. Due to the DC converter, the harmonic injection into the AC supply is reduced. In figure 16.11c, the DC voltage is varied by the dual converter and frequency is controlled within the inverter. This arrangement permits regeneration. However, the input power factor of the converter is low, especially at a high delay angle. So these are the uh, three different types of configuration. Example 16.6. Finding the performance parameter of a three-phase induction motor with voltage and frequency control. Something similar to the previous example, a three-phase 11.2 kilowatt, 1750 RPM, 460 volt 60 Hz 4-pole Y connected induction motor has the performance parameter here as shown. The motor is controlled by varying both the voltage and frequency. The volt-hertz ratio, which corresponds to the rated voltage and rated frequency, is maintained constant. Calculate the maximum torque Tm and the corresponding speed omega s for 60 and 30 Hz. B. Repeat A if Rs is negligible. So this is a solution. And from equation 65, Sm is equal to 0.1299, omega m is equal to 1566 rpm. From equation 21, the maximum torque is then obtained in this equation and has the value of 156.55 Newton meter. At 30 Hz, omega s is equal to 94.25 radian per second and beta is equal to 0.5. VA is then equal to 132.79. From equation 65, the slip for maximum torque Sm is now equal to 0.242. Omega m is equal to 682 rpm and Tm is equal to 125.82 Newton meter. At 60 Hz, omega b equal to omega s, which is equal to 188.5 radian per second, and the VA is 265.58 volt. From equation 60, Sm is obtained with a value of 0.1333. So this omega m is calculated as the value of 1560 rpm. From equation 59, maximum torque Tm is equal to 196.94 Newton meter. At 30 Hz, Sm is equal to 0.2666, omega m is equal to 660 rpm, and the Tm is equal to 196.94 Newton meter. Okay, it's quite long. It's not long, actually. It's a bit boring. Yeah, because just read through on it. Because for this chapter, there are too many equations here. Okay, which is during the time MCO, I was not able to do the normal teaching. Through this thing, I can only tell you based on the equation. Yeah, but I think it is okay. So at least you know there are numbers of this control technique in terms of the voltage, this frequency, and some others control parameter to control the speed of the given this motor. Yeah. So I think this will be the last part for our this chapter. So we have already ended